Still got some people to come, but we'll make a start. So we'll go back to our afternoon software theme. And I'm delighted to have Hugh Perkins here. First time to talk for the afternoon. Hugh's working in very interesting spaces, things very hot topics are going to come up. And in particular, I'm delighted he had this slightly controversial title mentioning the C word.
Okay, so this is about CUDA-on-CL, which is a compiler runtime for running NVIDIA CUDA C++ applications on OpenCL 1.2. Alright, so to start with a demo, as the slide says, we're going to run a CUDA application on Intel HD 5500. Actually, we're going to run on an Intel HD 530, but same idea. So here we've got command prompt. So I've got a Mac. You can't see I've got a Mac. Well, I guess you can see I've got a Mac. Okay, it's a Mac. So, and it doesn't have any NVIDIA left inside it. It's just got a Rally and then an Intel. So I'm just going to copy. It's a very simple CUDA script. So we can open it up. So it basically just got CUDA inside it. And what it's going to do is going to create a buffer on the GPU, run a kernel to set one of those values to 123, copy the buffer back to the host side, and then print out the value. That's what it's going to do. Okay, and so it's CUDA, right? So all we have to do is we do cockle simple.cu, off it goes to compiles, and we've got like this executable simple, and then we simply run it. Okay, and there we go, it's run, printed out 123. So that's running on an Intel HD 530. And I can also set an environment variable, which is just going to choose a different GPU. And there we are, it's running on a Radeon Pro 450. Okay. So that's the concept of running CUDA applications unchanged without any porting on an OpenCL 1.2 device. So the background to why. So NVIDIA CUDA is the language of choice for machine learning libraries. So that includes TensorFlow, Caffe, Torch, Piano. These are all written in CUDA. Now there are OpenCL ports that have been done by hand. Caffe was ported by Fabio and Schott, and by Julie Guertel, and by Robert Engel. Torch was ported by myself. There are also a few dedicated OpenCL libraries, for example DeepCL, Claret. Oops, wrong way. So why not port by hand? It's a maintenance nightmare. You have to fork the code. So you will have a CUDA code base, and you will have your OpenCL code base. And you cannot reconcile them. I mean, no one's succeeded yet. So for example, the Torch will be a separate repository from the core CUDA Torch code base. And it's feature incomplete, and it's frozen as of February 2006. So it would be nice to have some more automated way of handling this porting rather than porting it by hand. So here's the concept. We're going to leave the code in NVIDIA CUDA, and we're going to compile it into OpenCL 1.2. Right, and there's actually a whole ecosystem of kind of CUDA-like compilers. There's HIP by AMD, which can pretty much compile NVIDIA CUDA. You simply have to rename the API calls from being, for example, CUDA malloc to being something like HIP malloc. Is it portable? No, it's AMD only. Then we have two SQL compilers, which we know a lot about now, right? So the input to these is standard SQL, open standard, but you cannot just take a CUDA application and compile it with the SQL compilers. You would have to port it to the SQL, so you're going to port the code base. Is it portable? Yes, because it uses Sperm. I mean, when I say it, I mean Victor. The one from CodePay, the one from Rena. And then finally we've got NVIDIA CUDA. So of course NVIDIA CUDA runs on NVIDIA CUDA. Is it portable? No, it's NVIDIA only. Can you just compile it without needing to support it? Of course you can. Alright, and then CUDA-on-CL fits in here. It can take NVIDIA CUDA unmodified as its input, and it's going to use OpenCL 1.2 as its output. So you don't need any porting, and OpenCL 1.2 is widely available. Okay, so portability versus speed, this has come up a bit. So how do I see these different solutions in terms of portability versus speed? So this is not really based on anything objective, this is just how I see the world. So on the right hand side I've got speed, I put NVIDIA CUDA there, it runs quickly. Next to that I put HIP, because it runs on a single set of devices, which is AMD. And then I put the single solutions more towards portability, because they run on spare devices, which are fairly widely available. And I'm putting CUDA-on-CL right on the left, portability, but not so much speed. That's kind of how I'm aiming at. So how fast is CUDA-on-CL? So using CUDA-on-CL, we can compile vast swathes of TensorFlow, and we can run TensorFlow operations on an OpenCL device. We can also run those same operations on a CUDA device, and we can compare the speed. So what I've done in this graph is I've taken the speed for the CUDA-on-CL, the speed of the CUDA for each operation, divided them, and then we've got the ratio. So if it's 1, then the CUDA-on-CL and the CUDA run the same speed. So these are all run on an NVIDIA K80 GPU. It has to be an NVIDIA GPU, otherwise I can't compare across. So where these lines are a little bit longer, then the CUDA-on-CL is a little bit faster. Where the lines are a little bit shorter, then the CUDA is a bit faster. And I've done this for unitary operations, which is like hyperbolic tangent, binary operations, which is like power multiply, and then 2 types of reduction. And we can see that for the unitary, binary, and single axis reduction, actually the CUDA-on-CL is running pretty much the same speed as the CUDA. But there are 2 nuances. First nuance is, if you look in the top left, there's these little green lines here, right? Those green lines are full reduction. So we're taking a 2-dimensional matrix and reducing it down to a single scalar. And for the full reduction, CUDA-on-CL is 14 times slower than the CUDA. So that's nuance number 1. And nuance number 2 is also these are for really large batch sizes. So this is 500 megabytes, super large. So that high is the overhead of the boilerplate that we insert at the start of each kernel to handle the OpenCL 1.1 compatibility. So we can investigate a little bit more into the effect of batch size. So here we've got a graph of the effect of batch size on execution time. So the CUDA-on-CL is red, and the CUDA is blue. These are logarithmic axes. So on the Y we've got the time seconds, so this is like 1 millisecond, 10 milliseconds, 100 milliseconds, and 1 second. On the x-axis we've got the batch size in megabytes, so this is 1 megabyte, this is a gigabyte, and this is like 10 kilobytes. Okay? And what we can see is that for batch sizes of about a megabyte or more, the CUDA-on-CL is getting the same execution time as the CUDA, right? Running this TensorFlow. But as we go down asymptotically to a 0 batch size, so that we're looking at the kind of kernel launch overhead, there's a little bit of TensorFlow overhead here. But basically, something to do with, the difference here is going to be the kernel launch overhead. So the kernel launch overhead for the CUDA here is like a millisecond. That's probably including some TensorFlow time too. And the kernel launch overhead for the CUDA-on-CL is something like, it's like 2 milliseconds for the CUDA. And it's like 3 or 4 milliseconds for the CUDA-on-CL. So the launch overhead is like twice for the CUDA-on-CL compared to the CUDA. For the batch sizes of more than 1 megabyte, then that kind of disappears to nothing. We can do similar graph for the full reduction. So basically what we see for the full reduction is that it's consistently 14 times slower, whatever the batch size. So there's something at the level of each element, or maybe each row, that's causing a consistent slowdown. I don't know why, there's no opportunity to analyze why. So basically the CUDA-on-CL actually gives good performance on many kernels, but it's kernel specific. Some kernels are like more than 10 times faster. It depends on the kernel. Alright, so key design decisions of CUDA-on-CL. So first question is, we want to compile C++ 11 kernels. How are we going to do that? The second thing is, how are we going to feed bytecode to the GPU driver? And then the third thing is, how are we going to handle the NVIDIA CUDA API calls? Because if we want to run the NVIDIA CUDA code unchanged, we need to somehow handle the API calls. So the answers to these, as you can see in green. So we want to compile C++ 11 kernels. How are we going to do that? So we're going to use clang/LLVM. We're not going to use the compiler, but we are going to use the parser. So the parser is going to take the C++ 11 code, it's going to convert it into C99 bytecode for us. So that bytecode still contains CUDA, NVIDIA CUDA, but it no longer contains classes and objects. It contains like gotos and conditional gotos. So we've got rid of all the C++ 11 stuff. And then, so the next question is how to feed the bytecode to the GPU driver. So there's a few options here. The SYCL guys are going with SPUR 1.2 and then SPUR V. That has the downside that it's not ubiquitous. Because, for example, my Mac cannot ingest SPUR of any sort, as far as I know. So I decided to go with OpenCL 1.2, which is very widely available. For example, my Mac can handle OpenCL 1.2. So there's a certain amount of effort involved in generating OpenCL 1.2, but it does make it widely portable. And then the third thing is how to handle the NVIDIA CUDA API calls. So what we're going to do is we're going to implement the NVIDIA CUDA API in OpenCL. So that's the key design decisions. Okay, so we're going to look a little bit at the architecture. So this is how the kernel compilation looks. This is kind of a very high level, of course. Basically, we're going to take the CUDA kernel and we're going to use clang/LLVM to convert that into bytecode. So that's going to parse it for us. And then we're going to write an OpenCL generator which is going to take that LLVM IR bytecode and it's going to write it out as OpenCL 1.2. Slight nuance, so the parsing is done at compile time. So when you run the COCL compiler, it's going to parse the CUDA, the NVIDIA CUDA into the bytecode. The generation is going to happen at runtime. That's because we have much more knowledge about what types of objects, buffers, etc. we need to handle at runtime than we do at compile time. Looking more at compile time, this is a little bit more detail. So we've got the CUDA source code, NVIDIA CUDA source code. We use Clang, that converts it into bytecode. It's going to split the source code into two. It's going to split it into the host bytecode and the device bytecode, and Clang does that for us, so that's great. So that means we can have like our single source code going in. And then the host bytecode is going to be compiled into an executable via an object file, so you can link it together if you want. The device bytecode is going to be compiled at runtime. So we're simply going to embed it in the executable as a string. And we link the executable with the CUDA-on-CL runtime. Right, runtime, it looks something like this. Again, it's very high level, simplified, but approximately like this. So the user executable is going to make lots of calls to the NVIDIA CUDA API. CUDA-on-CL implements those NVIDIA CUDA API calls and handles things like launching kernels, virtual memory, creating contexts, handling query for devices and so on, and it's going to handle communicating with the GPU. So the kernel launch bit here is going to generate the OpenCL feedback. Okay, there are a number of edge cases and not so edge cases with trying to run NVIDIA CUDA on OpenCL 1.2. Because OpenCL 1.2 has a lot of restrictions. There's a lot of things that are allowed in NVIDIA CUDA which are not allowed in OpenCL 1.2. So how to handle those. Okay, now I don't have time to go through the details of all of these here because I've only got a certain amount of time. We will just pick one of these, which is handling the host side GPU buffer offsets. But I'm going to go through the other challenges that CUDA-on-CL handles. So the first thing is all address spaces have to be statically declared. So you have to declare any pointer in OpenCL as being global or local or implicitly private. And not only do you have to declare every pointer as being global or local or implicitly private, if you have a function call, you can only assign one specific combination of address spaces to that function call. But that function might be called from multiple locations in the program with different address spaces. I don't have to go into that, but CUDA-on-CL does do that. And OpenCL forbids by-value structs as kernel parameters, but CUDA doesn't. And in addition, you're not allowed to pass pointers in structs in OpenCL 1.2. But CUDA elapsed that. Also, the OpenCL 1.2 lacks a lot of hardware operations /. So I don't have time to go into how CUDA-on-CL solves these, but it does. But we'll look at one example, which is the host-side GPU buffer offset. So CUDA lets you do things like you call CUDA malloc, and you're going to get a GPU buffer. So that buffer is going to be allocated on the GPU. You receive a pointer which represents that buffer on the GPU. You can then pass that into a kernel launch, and that's going to assign that buffer to that kernel to be used. But you can add an offset. You can, instead of sending buff, you can send buff plus 128. This is perfectly legal CUDA. What that means is the buffer received by the kernel will be a kind of like offset by 120 bytes into the underlying buffer. Okay, now OpenCL does not allow this. So you can create a buffer in OpenCL using CL create buffer. And you can assign that to a CL mem, which is actually a pointer disguised as a non-pointer. But you cannot add an offset to that CL mem and pass it into the kernel. It's forbidden. So how to handle that? So CUDA-on-CL does this. Number one, we implement virtual memory. And number two, we're going to rewrite the kernel. Question?
What about using sub-buffers?
That's OpenCL 2.0.
Sub-buffers? No.
Oh, sub-buffers. I tried sub-buffers and they crashed for me. So I tried it.
There are some constraints on alignments.
Yeah.
So that I guess it will not work.
So
The alignment is not as strict.
No, but
So let's go to the next
one. You
diagram.
cannot generate the subbuffer of this offset.
So the thing is, so let's say that we try sub-buffers. How do we get on? I only got this computer like 2 weeks ago, so I'm still figuring out how that works. I don't know how to drag. Anyway, so we're sending a buffer to the client executable. The client executable can just add some offset to that. How will the subbuffer address that issue?
You create a sub-buffer with this offset outside of the big buffer, and you set kernel arg the new buffer.
The client-side code is in CUDA. It's not expecting to have to create subbuffers.
Yeah, but the parser that will do the translation from the CUDA to OpenCL will actually do OpenCL APIs, right?
Okay, I don't know the answer to that. I'll check with you about it. So there may be a simpler solution than the one that I think possible. So there might be a way to improve this. But yeah, so there might be maybe other solutions. Right, this is my solution. So I implemented virtual memory. So here's the user executable. It's going to request a buffer using like CUDA malloc. That goes to the CUDA-on-CL virtual memory system. It's going to allocate a CL mem, but it's not going to return that to the host side. It's going to store that in a virtual memory lookup table, and it's going to return a virtual address to the client code. The client code later on is going to launch a kernel. It's going to pass back the virtual address, possibly with some offset. Who knows? That goes to the kernel launch. The kernel launch is going to look up the virtual address. It's going to retrieve the underlying CL mem and the offset. Right, without having to modify the host site code at all. This was a big challenge for the cafe guys actually. They spent a lot of time like adding offsets everywhere. But this doesn't need any code changes. Right, and then the second part is we need to rewrite the kernel. So actually this is an OpenCL kernel, but the actual kernel is going to be an NVIDIA CUDA kernel, right? So we're already generating this anyway. So all we do is when we generate it, instead of generating it with a single pointer, we simply add an additional offset. Right? And we control both sides of the kernel launch. So that's easy to do. It is incredibly easy actually. And then we simply add a little bit of boilerplate, which is going to add this pointer to this offset and get the pointer into the buffer. So for example, TensorFlow allocates a huge, like 2 GB block memory, and then just let offsets into that. So that's kind of necessary, otherwise you can't do anything out of that. So this is completely transparent and doesn't need any changes to the speed source code. So I seem to have radically undershot my time. I don't know how. Anyway. Right, open issues. So execution speed. So NVIDIA compile optimizations are really good, and we don't have access to this because they're privately locked away. So I pass OpenCL to a GPU driver, and it's going to optimize it, but are those optimizations going to be good as NVIDIA? It depends. Number two, OpenCL 1.2 compatibility boilerplate increases the launch overhead, as we saw. And number three, the OpenCL kernel launch times are intrinsically fairly high, which is why we had the thing like the zero launch thing last year, for example. And number four, there's some missing hardware implementations like traffic. Portability. So in theory, the OpenCL 1.2 can run everywhere. In practice, each kind of driver has different quirks. Some of these quirks are technically within the OpenCL 1.2 standard. Some of them might be slightly outside it. But the CUDA-on-CL stresses the drivers in unusual ways from the way it generates the code. So I hit a lot of bugs that other programs don't hit. So basically I need to test each platform case by case. So I run it on like Intel and NVIDIA, and since 2 weeks on Radeon, but that's yeah. So overall, so CUDA-on-CL actually works on some fairly complex kernels. So I can compile and run eigenkernels, compile and run large swathes of TensorFlow. It runs on multiple vendors' GPUs, so it runs on NVIDIA GPUs, tested on Intel HD GPUs, and now I'm testing it on Radeon. Execution speed can be at parity with native NVIDIA CUDA, it depends on the kernel. And it's a much more general solution than putting by hand. So it's open source under the Apache 2.0 license, and you can download it. Yeah. That's it, yeah.